Good evening to all. On behalf of the Department of Mathematics, Queen Mary's College, I wish to extend a warm welcome to our resource person, Dr. Robinson Tamburaj, Associate Professor and Head of the Department of Mathematics, Madras Christian College, Tambaram, and all the participants who are joining us live from across India and abroad for this webinar on Introduction to the Theory of Automata and its Applications. We had received around 745 registrations from all districts of Tamil Nadu, including Chennai, Coimbatore, Trichy, Madurai, Kumbakonam, Tirunelveli, Nagarkoil, Kadalur, Chidambaram, and so on. And from various other states running from north to south, like Punjab, Uttar Pradesh, Maharashtra, Odisha, Telangana, Karnataka, and Kerala. We also had a registration from the US and Zambia too. I hope you are all joining us live now and would be benefited by this webinar. As we all face this pandemic and understand that there is no going back to the normal soon, we should have a new way of changing our focus into the new normal. And I'm sure these virtual webinars are equipping us for this new normal. For those of us who are joining the webinar with an eagerness to know what this automata theory is all about, I would just like to give a bird's eye view of the topic, which will be explored by our resource person in a few minutes. Automata theory is an exciting theoretical branch of computer science, which deals with the study of abstract computational devices and machines referred to as automata, as well as the computational problems that can be solved using them. Through automata, computer scientists are able to understand how machines compute functions and solve problems, and more importantly, find out what different models of machines can do and cannot do. So, the motivation behind the study of automaton is that it has different application to creating compilers and programming languages. It is a formal framework to analyze new types of computing devices such as biocomputers and quantum computers. I'm sure our resource person will take us all on a journey through this theory of automata. I would just like to remind you, please use the chat window only towards the end of the presentation to post your questions so that the resource person can go ahead undisturbed. A few minutes will be given after the presentation to post your questions in the chat window, after which the feedback link will be given to us. So let's sit back and enjoy the lecture. Now, our head of the department, Dr. M. Vijaya, will introduce the resource person, Dr. Robinson Tamburaj, to us. Over to Madam.
Thank you, Emerald. Good evening to all. I feel very happy to welcome our resource person, Dr. Robinson Tamburaj sir, for the webinar on Introduction to the Theory of Automata and its Applications. I am privileged to introduce our resource person, Dr. P. Robinson sir. He is an associate professor and head of the Department of Mathematics, Madras Christian College, Chennai. He obtained PhD from the University of Madras in 2001 for his work on picture languages in the area of computer mathematics. His research interest includes automata theory, image analysis, nature-inspired computing, tactile geometry, and inclusive education. He has published about 80 research articles in reputed journals and authored many books. He has been guiding PhD and MPhil research scholars in the area of automata theory and image analysis. Ministry of Social Justice and Empowerment, Government of India conferred him with a national award in 2005 for his contribution in the field of welfare of persons with disabilities. Chosen by DST, Government of India, and the Japan Society for Promotion of Science, Japan, he pursued and obtained PhD in the area of disability science from the University of Tsukuba, Japan 2007. He also received Tamil Nadu Innovation Award in 2009, conferred by Confederation of Indian Industries, Chennai. He was conferred by the Welfare Foundation of the Blind, Chennai, as Friend of Blind in 2004. Dr. Robinson was the recipient of Leverhulme Fellowship for his postdoctoral research during 2009-10 at the Liverpool Hope University, United Kingdom. He co-organized the 5th International Conference on Bio-Inspired Computing, Theories and Applications held in 2010. Certified and trained by Center of Excellence in Science and Mathematics Education, Indian Institute of Science Education and Research, Pune. He is a workshop trainer for college teachers on research-based pedagogical tools. He is currently the coordinator of IQAC in the Madras Christian College, Chennai. We have with us an eminent professor in automata theory. Let us all enjoy and enhance our knowledge from his lecture. Thank you all. I hand over the session to Dr. Robinson Tamburaj, sir. Welcome you, sir.
Thank you very much, madam. Thank you for those nice words. Hello, everyone, and good afternoon to everyone. COVID-19 is a game changer. It has changed the way we've been working or thinking. It is offering so much of challenges and hardships to many. But the academic community has turned these challenges into opportunities to find alternative means for teaching. My heartfelt appreciation to Dr. Varalakshmi Anandkumar, the principal of Queen Mary's College, Dr. Vijaya, head of Mass Department, for this special initiative. I want to thank the coordinators, Dr. Vasanthi Beulah and Dr. Emerald, for making this possible. And my special thanks goes to Mr. Jonathan Solomon for rendering his assistance in the technical side. And I'm going to share the screen. Well, I hope you all are seeing the first slide with the title Introduction to the Theory of Automata and its Applications. Well, as the title says, my talk is of introductory nature because the intended audience group includes largely students who want to have a primer on automata theory. Before I start, I request the participants to be ready with a paper and a pencil so that you can work out along with me in some of the examples. For your queries to be answered. In case we have more queries, then I will show my email ID or WhatsApp number. You can post your queries through those means as well. Are you ready? Shall we begin? Okay. Automata theory. What is this theory? And how it was all started? The very notion of automata or automaton comes from the mathematical logic or linguistics background. When people are trying to explore how the neurons in the brain function, they communicate with each other. And it is due to Mr. Alan Turing, the mid-1930s, who gave the formalism of how algorithmic concepts and machine models can be developed. He was very much a mathematician, a logician, a cryptanalyst, because he worked in the British code-breaking company for a while. And this study of automata is very fundamental to the computer science. And so Alan Turing is sometimes referred as father of computer science. Okay, the study or the area of automata theory helps us to understand the capabilities and limitations of various computing devices, which you call automata, and helps us to kind of design better algorithms or efficient algorithms in terms of speed and space, time and space. Well, the very word automata, of course, is plural, automaton singular. It means an abstract computing model or a mathematical machine model which performs a sequence of operations. Right. I was wondering how should I start this talk. Then I decided to choose this conjecture, which is famous in the theory of automata, which is called the Church-Turing thesis. It says that any computation that can be carried out by mechanical means can be performed by some Turing machine. It's a conjecture. Well, and here you find the term Turing machine. What is a Turing machine? Well, to recognize the contribution made by Alan Turing, the highest machine model is given the name Turing machine to honor the contribution of Alan Turing. Well, how does a Turing machine work, or how does it compute? Can a Turing machine solve or compute any kind of problem, or does it have any kind of a limitation? How do we understand this computing device? Do we have any simpler approach to understand this machine model? Well, this talk is about that only. Well, let's just start with few illustrations. Can you think of a device or facility that gives money to customers in financial need at any time of the day? Yes, you got it right. The ATM machines, or ATM. These are basically small kiosks attached to banks, which you find in many spots in the city or towns. Basically, they facilitate in financial transactions to withdraw cash or to deposit money or to do the money transfer or to get the account information, etc., at any time of the day or night. Yes, but how does ATM function? Well, how do you get the cash from this ATM, these machines? You must be having a debit card or a credit card. You go to the machine. There's a slot where you can insert your ATM card, and then you got to press a sequence of the pin numbers or buttons, and then ATM process all those sequence of the commands or the buttons that you pressed, and then you get the cash. In case the machine runs out of money, it gives you a small message, no cash or come later. Fine. Few more illustrations. Can you think of a system or a method that verifies if the given integer is even? Well, suppose I give you a number, say 20, and I'm asking you to kind of find out whether it's even or odd. What do? You take the number 20, then immediately you divide by 2. If you get remainder 0, then you are sure it's even. Suppose I give the number 7. You divide by 2, you don't get remainder 0, and so I decide it's not even. So there's a method that verifies if a number given is even or odd. Do you have a method or a technique that verifies if the given number is a prime? Well, the same way, the primality testing condition is there to check whether the number is prime or not. How about if I give a bunch of codes, is it possible to find a system that verifies that that bunch is a Java codes? Yes, we have the Java compilers. When you write all those codes, the compiler will verify whether it is all valid set of codes or not. So the point is, when you have a question or when you have some data, and when you have a method, the data is processed. And at the end, you have some outcome, some output, yes or no, okay or not okay. Fine. Now, I want to bring your attention to this picture. Here you find a man or a farmer who is standing on one side of a river with a wolf goat, and a cabbage. And also you find a boat there. Now, I hope you all can recall this famous riddle. Now, I want to switch over to the internet and play this video for you.
This is the most common river crossing brain
Well,
teaser.
there's a farmer who is returning
A
from
farmer
city
was
to his
returning
village,
from the city to his
and
village.
he has to
The
bring
farmer had
a
bought a
cabbage,
a goat, and a
bunch,
cabbage
wolf,
for his
goat
family.
across the river to his home.
There was a 50-meter
But the river
wide
is quite
river in
wide,
his path to his village.
and he's got a small boat which he
Fortunately,
can row.
a small boat was on the
But
city
the
side
thing
of the
is
river.
that he cannot take
But
more than
here's
one
the
object
problem.
when he is rowing the
The
boat.
farmer calculated and found
So
out
how does
that the
he kind
boat
of
could
transport
support
all these
only
three
one more weight
articles
other than
from
himself.
the right side of the river to the left side
Also,
of the river?
if he leaves the
Suppose he
goat and
takes
the fox
wolf
at
and
any end alone,
goat.
the cunning fox
Well,
will
wolf
kill the
is
goat.
carnivorous; it can simply eat the
On the
goat.
other hand,
If he
if he
takes
leaves the
goat
goat
and
the
cabbage, well,
at
goat is
any end, the
herbivorous;
hungry
it can
goat
simply
will
eat the
the
cabbage. So he's wondering how
How will
to
he cross the
transport.
river with all his belongings?
Well, so he naturally
The first step
chooses
is obviously simple.
the goat
As
first,
he cannot
takes
take
the goat
anything
in
with
his
him
boat,
other than the goat,
and rows
first
across the
trip will
river.
be with the goat.
He drops the goat on the left side.
He
When
leaves
he comes
goat
back,
at the village end
this
and
time
goes back to the city
he's going
end.
to pick up the cabbage,
Here,
then
he carries
rows
the
back
cabbage with
to the left
himself
side.
and makes the second trip to
He's
the
placing
village
the
end.
cabbage here, but immediately he picks up the goat from
At the
that
village
side.
end, he drops the
Now he
cabbage there
transports
and
goat
makes
to
the
the right
goat to
side,
jump onto the boat and rows
and
back to the
naturally he's going
fox.
to pick up wolf this time, but drop goat there
The fox is then made
for safety.
jump onto the boat,
Now he comes
and
back,
the goat is left there.
puts the wolf here. The wolf cannot eat
The
cabbage.
farmer then leaves the fox with
Comes
the cabbage
back.
at the village
This
end
time,
and
of course,
makes
he's
his last
picking up the
trip
goat
back to the city end.
and bring back the goat to the left side.
He then takes the
And
goat
so
with
once this is
himself
done, all the
rows
three
back to the
articles
village
are
end.
safe along with him.
The problem
Well,
is now
this
solved.
riddle is very simple and well known. Let's I had already put the question. Can you think of a method that solves this challenge this farmer faces? Yes. Well, let's try to kind of put some notations, some symbolism. I'm just putting a small oval-shaped circle. I'm writing E-MWGC, which means the left side is empty, whereas the right side is having man along with the wolf, goat, and cabbage. This is the starting scenario. At the end, all the four articles on the left side, man, wolf, goat, and cabbage, while the right side is empty. So basically, the starting is the problem, the riddle, and at the end, this is how it is solved. But how that is solved, this is how it is solved. There are basically 8 stages involved. And he's transporting goat, cabbage, wolf. He's shuttling from right side to left side. So basically, there are 4 types of transporting. And he's shuttling 7 times. I'm using some notation, small g, for transporting goat across, small c for transporting cabbage across, w for wolf, and man alone, just m. So from the start to the finish, there are 8 stages and some transitions from first scenario to the last scenario. So if a system performs this kind of steps, the problem or the riddle is solved. Okay. I want to kind of give some, well, this is what I have already said. Now let's get back to some basics, some few preliminaries we want to kind of recall. In the automata theory, the basic unit is a symbol. What's a symbol? Symbol is nothing but a character. It can be a character like A from the English language, or B, or the symbol at mark, or the number 5, or a symbol, the dollar symbol. It can be any character which occupies, of course, 1 unit of space. And By alphabet, we mean a finite collection, a finite set of symbols. For example, if a group A, small a, B, C together, those three elements, the forming a set, I can call it alphabet and give some name, say capital A. Suppose I want to choose the number 0 and 1, call it a set. I can call it an alphabet with the name, say capital B. Fine. From an alphabet set, I can make out something called a string or a word. By a string, I mean a sequence of symbols from an alphabet. For example, if you take the first alphabet, say capital A, that is ABC, I can make out some string A, B, C, A, B, C, B, B, A, A. It's basically a string, a sequence of symbols drawn from the set A. The same way, I can talk about another string 0, 1, 0, 1, 0, 0, 1, 1 from the other set. This is a string from the set B. Well, these are called strings or words. Fine. We can talk about length of a word, length of a string. With the same string, A, B, C, A, B, C, B, B, A, A. If you just count the number of characters or symbols, you find 10 are there. So the length is 10 here. In the case of the second string, 0, 1, 0, 1, 0, 0, 1, 1, it has got 8 symbols. So the length is 8. Well, can you think of a word with the length 0? Well, mathematically, it should be possible to kind of define a string of length 0. Such a string or a word is called empty word. The empty word is a string or word of length 0. When it's of length 0, you have nothing to see there. So we have to use some notation. We will either use epsilon or lambda to represent an empty word. Because you can't see an empty word, you have to use some notation to represent that. So we'll be either using epsilon or lambda. Okay. Now coming to the third important definition, a language. It's called formal language. What's a language? Language is a set of strings out of an alphabet. We have already seen what's a word or a string. And now collection of strings. For example, if I take a string of length to AA and another string of length to AB, BB, BA. So I have very specifically chosen 4 strings, each of length 2. I'm calling it a set. This set, which has got only 4 elements, no harm in calling it a language. So language is a set of strings. Second example, here I got the string 0, 1, another string 0, 1, 0, 1, then 1, 0, 1, 1, 1, 1. It goes on. I don't stop there, which means the set is infinite in nature. Well, it's an infinite language. So a language can have finite number of strings or infinite number of strings. You might wonder, how about a word? Can a word be of definite length like 10 or 8, or can it be also indefinite? Well, it is possible to define words of infinite length, infinite word. But in our study at the moment, we don't worry about infinite word. We only focus on finite words, words of finite length. But a language could be finite or infinite in size. Fine. Now, one more notation is very, very important for us. Let's just take the string A, B, B, C, C. What's the length of the string? There are 6 symbols, so the length is 6. The same string can be expressed in this form because I find 3 copies of A, 2 copies of B, and just 1 copy of C. The same string can be expressed as A cube, B square, and C. Please note that this is not the arithmetic operation in the language theoretic sense. 3 copies of A, 2 copies of B, and just 1 copy of C. I don't have to put the C power 1 there because when I have a C, it's understood that C is just 1 copy. Okay. Let's move on. I'm going to take an alphabet with just two symbols, A and B. This being a set, you can call it as an alphabet, and I'm giving a name of the alphabet sigma. So sigma is an alphabet with just two symbols, A and B. Now listen here, I'm using sigma power star. This is a special notation. For any alphabet, say sigma here, if I put power star, it indicates that set of all possible strings of all possible lengths. For any alphabet, the power star would indicate set of all possible strings of all possible lengths out of that alphabet. Well, here I have A and B as two symbols. I can think of the very A here, the very B here, then A, B, B, B. Then I can think of three words of length 3, A, B, then A, B, A, all that. Then strings of 4 lengths, 5 lengths. It goes indefinite. The same way, I can think of words of length 2, 1, and 0. That is lambda, empty word. So by sigma star, I mean all possible words or strings of all possible lengths. Okay, let's have that as a big set. Now, I'm going to choose few words from this big set. I'm choosing B and putting it here. I'm choosing AB and putting it here. Choosing BB, putting it here. So I'm just kind of picking some words from this large set and I'm calling it as set S1. You may recall that a set of strings is called a language. So this set, I can call it a language. The name is S1. Here I'm having another set with a different collection of strings. You find only A, single A, double A, triple A, 4 A's, and so on. So I've decided to kind of choose a set with some special feature of strings. It's a different set. It's a different language. I may call the name S2. Well, this language, it is possible to express in the notation A. The A is nothing but A square. A is nothing but A cube. So I'm just trying to put in the notation form. Then I find that the power is varying 2 here, 3, 4, 5, 6. So the whole thing I can capture in a nutshell like this, A power n, where n is a natural number varying 1, 2, 3. This is easier to express this set, very compact expression, compact form. So I can very well say that this language S2 is nothing but the same, A power n ranges from 1 onwards. So it's very nice to see the whole language expressed in a very compact form. Let's take another language, S3. This has got the strings AB, 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 AB. So you're able to find that the AB is kind of occurring once here, twice here, thrice here, and so on. So I can very well express that language in this way or in a compact form like this, AB the whole power n. That means AB is occurring n times when n varies from 1 onwards. Okay, so this notation is very helpful when we deal with languages. Okay, some more examples. Let me have another alphabet, say 0 and 1. From here, I'm forming a language, say call it S4. In this language, what do you find? There is some feature you can note. You find that every string here ends with a 1. Well, you find that this language has a specialty. It is every string is ending with 1. What about the second example, the language S5? You find every string here is ending with 0. Fine. So it is possible for languages to have their own specialty, their own features, which is common to all the words in that language, in that set. What about this language. 01, 0011, 000111. You find that n copies of zeros and then n copies of ones. So 0 power n, 1 power n. This is a language. This is a feature of all the strings in this language. One more example. Here you find, as you see, you're able to find that every string can be read from left to right or right to left, which means they are the same, which means they are the palindrome strings. So this can be another language, the set of all palindromes from the set B. So it is possible to think of languages that have very special features that run across all the members of that same language. Now let's go back to the same riddle where we left. We mentioned that the farmer can transport all the articles from right side of the river to the left side of the river if he follows this order. Okay. Now, this is basically a method of solving that riddle. If you can think of a system, a machine, which can follow these instructions, the machine can very well solve this riddle. Fine. So the same problem, I'm just giving different notations or different labels. Instead of calling this A, M, W, G, C, I'm just giving Q1, Q2, Q3 up to Q8. And I want to call these 8 stages as set of states. And you find there are 8 stages. And there are 4 types of the transporting goat or cabbage or wolf or man alone. I'm using these 4 simple symbols. Mind you, I'm using the word symbol here. So I can call them as input triggers. These symbols will make you move from one state to the other state. Suppose you are in state Q1, and this arrow, this transition will make you move from this state to this state. And then M will make you move from state Q2 to state Q3. So basically G, M, C, G, W, M, G. This sequence of symbols, or if you take that string, G, M, C, G, W, M, G, is basically a string of 7 symbols, a string of length 7. If you follow this string from the start stage, you are sure to reach the finishing stage, solving the riddle. Okay, so that's what we have mentioned here. The start stage is Q1, the last stage is Q8. Okay, now we are ready to define formally the simplest model, machine model called finite state automaton. I already told you that if you can find a system which follows this instruction, it can solve the riddle. And that system hereafter will be called a machine. In fact, I'm going to call that name finite state automaton, FSA in short. What is an FSA? FSA is the simplest machine model that has got the 5 components: set of states, which we call Q, set of input symbols, you can call sigma, set of the transitions. Well, there is, if you are in one state, if you take one input symbol, you are free to move to another state. At this moment, don't worry about this function. Basically, we have the transitions, moving from one state to the other state. And how you begin the whole process, you have to have a different start. And Q1 is, I made a mistake here, Q1 is a start state. And it has to end by reaching some final stage. That can be one or more than one way you stop. In this example, there's only one way of stopping. So the set of final states, F. So in our example, there are 8 states. There are 4 input symbols. There are 7 transitions. Q1 is a definite start state, and Q8 is a definite final state. Okay. Now, let's have some small exercise. I'm talking about a language, L1. That language has only one member, only one string A. Can you think of a machine or a FSA that can recognize this as its language or output? How do we do that? Let's proceed. So we want to construct a machine that will recognize or that will accept exactly the language L1 specified. How do we do that? Our machine must have a start state, it must have stop state, and it must have transition. You find that A is the input trigger. If you have this input trigger, it should make the machine move from one state to the other state. In fact, if this input trigger is making the machine move from a start state to reach the final state, then you can call that as a successful transition. In this case, this string, which is one symbol, is making the machine move from the start state to the final state. How do I know that Q1 is the start state? I'm using a very special notation here, an incoming arrow, which means that this is the start state. And how do I know this is the final state? I'm indicating with a double circle. So that's the notation we are using. In any FSA, an incoming arrow to a state would mean that there is a start state. And any state that has double circle means that it's a stop state or a final state. So in this FSA, there are two states, Q1 and Q2. So which I call set of states, Q1 and Q2. And there's only one input symbol, sigma, capital sigma is A. And there's only one transition from Q1 to Q2. So this is how I write. Delta is a mapping. That is, when the machine is in state Q1, when FSA in state Q1, upon taking the input A, the machine is moving to state Q2. There's only one transition, and so we have one transition expression here as a mapping. The start state is Q1, which I indicate here. The stop state is Q2, which I indicate here. So this FSA, I can give a name, the machine M1. It has got the 5 components, Q, sigma, delta, Q1, and F. Let's take the second example. We want to find another machine, another FSA, to recognize the language L2 exclusively. This language L2, the name of the language, has got 2 elements, 2 strings. The first element is just a 0. The second string is made up of 3 symbols, 1, 0, 1. Now I must find a machine that will start and end. When it reaches the end, it has to either recognize this string and or this string. Okay, so in the earlier case, we had only one string, one element. Here there are 2 strings, 2 different strings. So I must have some states. Let me say that Q1 is a start state where the whole machine begins its operation. To recognize this string, it has to start at Q1. It has to have 0 as the input. And then as soon as the 0 is taken as the transition, it has to reach a final state. So what do? I am making a state here, Q2. I'm making it compulsorily a stop state because from Q1 upon 0, you reach Q2. Then I designate this as the final state. By doing, I make sure that Q1 to Q2, a start state to final state is reached through this input 0. Now, there's one more word to be recognized by the same machine. So what do? I have to again start from the start state Q1. This time I have to go a different path that will give me this sequence of symbols. And for every symbol, there has to be one halting in a state. And there are 3 symbols. So definitely there must be 2 intermediate states. So I give a different name now. Q2, Q4, then Q5. Now you find for each transition, I'm having the symbol 1, 0, 1. And I'm making Q5 as another final state. You may note that Q1 is a common start state. Here's a branch. If you go by this branch, the machine is moving from state Q1 to state Q3 through Q4 and reaches the state Q5. And here, Q2 and Q5 are two different final states. So if the machine is taking this path to reach the final state, it is recognizing this string. When the machine has the free will to choose this path, it is recognizing this sequence of symbols, which amounts to 1, 0, 1, which is the second string. So basically, this language talks about all possible paths from start state Q1 to any of the final states. So to summarize, I have a machine, I may call it by name M2. The set of states are Q1, Q2, Q3, Q4, Q5, the 5 states here. I should have mentioned Q1, sorry. I should have mentioned Q1, Q2, Q3, Q4, and Q5. It should have been Q5. Sorry about that. And there are two input symbols, 0 and 1. So 0 and 1. There are 1, 2, 3, 4. There are 4 transitions. So you find delta state Q1 while taking 0, it has to go to Q2. So delta Q1, 0, Q2. Delta of Q1 on 1 goes to Q3. So you find those 4 transitions expressed here. The start state is Q1 and final states are Q2 and Q5, which you mentioned here. So I'm able to express the FSA that recognize this language. Well, there are some more languages here. This language, which we have already mentioned, A power n. How do I find a machine to accept this language, which is basically infinite in nature? Well, let's get on this whiteboard. This is my language, A power n, n greater than or equal to 1. That means it has got A, 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 and so on, infinite. There are infinitely many strings. Look for the smallest string or the simplest string, A. We know how to construct a machine to accept just the symbol A. It must have a start state, say Q1. It must have a stop state, say Q2. And there must be an arc from Q1 to Q2 carrying the symbol A. So when I draw this machine, it is able to start at Q1, recognize the symbol, and reach final state. But this machine is not sufficient because it can recognize only one symbol, only one string. I must have a machine that accepts this, all this. So what do? I can introduce a loop here. That means Q1 on A, I can take this A for first A, then come via this arc to reach second A. If you want to recognize A, take the loop 2 times, once, twice. The third time, you take this arc. So at the end of reading the 3 A's, you're able to reach the final state. How about the word A? For the first 3 A's, it will kind of take the loop 3 times. For the last A, it will take this arc to reach Q2. So at the end of the 4th A, it has reached the final state. Is that clear? Okay. Coming to the 4th example, A power n, n greater than or equal to 0. What does language mean? This language, the previous language, we had A power n, n greater than or equal to 1. That means when n equal to 1, you have A, then A, and so on. Here, A power n, n greater than or equal to 0. That means A power 0 would mean the epsilon, empty word. And then when n is 1, A, and so on. So this set is slightly bigger than this set with one more word, say empty word. How do I find a machine to accept this? Well, let's make use of the same, the previous machine, FSA, Q1, Q2, where Q1 is a start state. And from Q1 to Q2, we had A. Then we had a loop from Q1 to Q1 on A. We said that Q2 is a final state. Okay, lambda is an empty word. That means for empty word, it should start at the start state and reach a final state. It is possible when I declare Q1 also as a final state. When I declare Q1 as a final state, that means you just start at Q1. For reading nothing, you can stop there. And so to accept this language, Q1 and Q2 both are final states. Q1 is a start state as well as final state, and Q2 is another final state. Is that clear? Okay, let's move on. And here this time, the fifth language, L5, a power n, where n is an odd non-negative integer. That means a power n is basically 1, 3, 5, 7, and so on, all the odd powers of natural numbers. That means a, and then 5 a's, and so on. In infinite language. The smallest is this one. We are very much aware how to find a machine, FSA, to accept that simple string. Q1 is the start state, Q is the final state. But this is not sufficient because there are plenty of other words. Now I should make the machine accept a cube, that is AAA. If I put a loop here, it will accept a square, which is not in the language. It is not correct. I should have my machine tailor-made for this language. So what do? I can think of an arc this way. So now for the 3 A's, first A, second A, third A, at the end of the third A, I'm reaching the final state. How about the A power of 5? First A, second A, third, fourth, fifth. Yes. So this machine works very well. Okay, sorry about that. The next example is this one. Language L6, 0 power n 2. That means n copies of 0 followed by a 2. N is greater than or equal to 1. That means it has to have any number of zeros followed by 1, 2. So which is the smallest word string here? Just 0, 2, then 0, 0, 2, and so on. Let's have state Q1. Because the length of the string is 2, I must have 3 states. Q1 is the start state, Q1 to Q2 with 0, Q2 to Q3 with 2. I will declare Q3 as a final state. Now this machine is able to accept or recognize the string 0, 2. Now, you know how to make recursive or repetitive nature because zeros are occurring many times. I can well introduce a loop here for 0. Then I can get any number of zeros, but minimum at least 1 0 is there. So this machine can very well accept the language 0 power n 2. Other option, suppose you had thought of having your loop here for 0, that's also perfectly fine. It's other machine. Both are accepting the same language. So the point is, for a given language, you can have more than one different type of machines. Okay, that's one more example you can try at home. Then there's a note here. any language that is recognized or generated by FSA, you can call that a regular language. So in that sense, all these languages, L1, L2, L3, all these languages can be called regular languages, because for each language, you can find at least one FSA to recognize that language. Let's move on. Now, we have given the formal definition. Now we move on to the informal description of a FSA. When we say informal, it helps us to develop a mental image about the machine. We are able to kind of have this picture in mind. Now, let's have the same five components of a machine: FSA, Q, sigma, delta, start state, final state. You have to develop this picture in mind. You have to think of infinite or kind of input tape, which has got many cells. In each cell, you can store one character or one symbol. It must have a control unit from which a small pointer is protruding, and this pointer can point at one symbol on the input tape, one symbol at a time. And this pointer can only scan and read the content of the cell. After scanning or reading, it can just jump one cell to the right on the tape. The control unit has all the transitions stored here. So this will behave as per the transitions described in the machine. At the end of processing the input, because we are supposed to place the input string on the tape, the machine can scan one symbol at a time. At the end of scanning, if the machine reaches a final state, the whole word is said to be accepted. Okay, let's have an example. We want to find a FSA that will accept this language. Well, we are familiar with this kind of diagram, which is called state diagram. Well, you find n copies of zeros, a single 2, and m copies of 1. And n and m can independently vary from 1 onwards, which means I can have 0, 2, 1, 0, 0, 2, 1, 0, 2, 1, 1, all those. Look at this machine here. Start state is Q1. And end state is Q2. This is basically n and m greater than or equal to 0. Okay, please read that as 0. That means if it is 0, then n will be 0, m is 0, the least is 2. So you're starting at Q1, on scanning 2, it stopped. Then for n copies of 0, you have this loop that can take care of n copies of 0. And for m copies of 1, this loop can take care. Now, so we can have this machine expressed this way. 2 states Q1, Q2, and 0, 1, 2, the input symbols. So this is basically a set of states, set of input symbols, and there are 1, 2, 3. There are 3 transitions, and Q1 is the start state, Q2 is the final state. Let's see. I mean, the same thing I can express in the table form. The machine has Q1, Q2, 2 states. On reading 0, you can go to state Q1. On reading 2, you can go to state Q2. This is what I mentioned here. On reading Q1, it goes to same state Q1, or on reading 2, you can go to state Q2. And while in Q2, on reading 1, it can remain the same state, Q2 and the same state. Now let's just kind of this image in mind. We have an input tape, and I just want to test run the string 0021. 0021 is very much member of this language. When n is 2 and m is 1, this is very much in this language. So if I feed this input in the machine, let's see how the machine behaves. So what I'm supposed to do, I have to keep that input string on the input tape. It has got length 4. There are 4 symbols, so it's occupying 4 cells. And this B stands for blank. Okay, I'm just using the small b to represent blank symbol. Okay, now when I start, I have to keep the pointer on the leftmost symbol of the string, 0. And the start state is Q1. Well, Q1, on scanning 0, it is supposed to move it has an option. It can be in the same state or move to Q1. So it is using this option. It remains the same state. And now the pointer head after scanning can jump to the rightmost. Look carefully. Yes. And now it is state Q1, scanning 0. It can remain there, or it can jump to state Q2. That's what it does. So while in Q1, scanning 0, it I come again. While in Q1, scanning 0, it remains in Q1. For second 0, while in Q1, scanning 0, it remains the same state Q1. So now it is in state Q1, scanning at 2. So while in Q1, scanning at 2, it is allowed to go to state Q2. Now, state Q2. And while in Q2, scanning a 1, it can remain the same state. And now, at the end of scanning the entire string, it is just jumping off the string. At that time, it has to check which state it is. It is state Q2, which is the final state. So the FSA is entering a final state at the end of the string. If it is so, then the string is said to be a part of the language. It is said to be accepted. Suppose I choose a word which is not the language, 0020. It is not there in the language. Why? Because I have 002, and suppose I have a 1 here, not a 0. So this string is not in the language. So if I feed this as input to the machine should not accept this string because this string is not in the language. The machine is designed for that language specifically. Let's see how it begins. Well, in 0, Q1, it remains the same state. For the 0, the same state. While 2, scanning 2, it goes state Q2, Q2. And now, while scanning the 0, while in Q2, scanning 0, nothing is mentioned here. No move is mentioned here, which means it is not defined what the machine is to next. So the machine is unable to finish reading and jump off the input string. The machine is unable to stop. It's simply hanging there. So the word is not completed, and so the string is not accepted because FSA is unable to reach a final state. Let's have, okay, so now what do? I'm taking the same machine and I'm giving a different language here, 0 power n to 1 power n. What's the difference between this language and this language? In this language, the zeros and ones can independently vary. When I have 5 zeros, I can have 7 ones. When I have 100 zeros, I can have 2 ones. Because n and m are independently, they can vary. Whereas here, I have n copies of 0, 2, then exactly the same n copies of 1. Which means when I have 4 zeros, I should have 4 0, 2, then have 4 ones. Let's see how can we find a machine. So I have Q1, Q2, start state, and well, is 2. Suppose I have a loop here for 0, a loop here for 1, and if I declare Q2 as a final state, I can have a number of zeros through this loop, maybe n copies of 0. Then when I come through this bridge, 1, 2, then here I can have any number of ones, not exactly a number of ones. There's no control. I have the freedom to choose a number of times. I'm not supposed to stop exactly because I have no control. The machine doesn't know it should stop exactly the n copies because the machine cannot remember, cannot keep track of how many zeros it had scanned so far. Because of that, the machine FSA has a limitation because it cannot remember how many zeros it had recognized so far. It cannot recognize that number of ones. So the limitation of FSA, due to its lack of memory, the FSA cannot recognize this language. Well, before we move on to the bigger machine, let's just have to kind of talk about determinism in the FSA. A machine is said to be deterministic if the machine can be in only exactly one state at any given time. If the machine can be in more than one state or no state, the machine is said to be non-deterministic. For example, let's just take this. Well, this is the input symbol. This input state. You find that for every state and for every input symbol, there's exactly one response. While in state Q naught scanning as 0, it goes to Q naught alone. Where it is, well, in state Q naught for 0, exactly Q2. Well, Q naught for a 1, exactly 1, Q1. So you find that exactly one response at any state for any symbol. This is called deterministic FSA. So look at this example here. For while it's in Q naught, for a 0, it can be in Q naught or you can go to Q1. There are two options, either go to Q naught or Q1. Well, in Q1, for 0, nothing is mentioned. Nothing is mentioned. So when you have multiple options or no option, the machine is said to be non-deterministic. Well, this is an example of the non-deterministic FSA, or as they call NFA. It is possible to convert any NFA into DFA, something called subset construction. Well, we don't spend time on that now, but for this non-deterministic FSA, there's the corresponding deterministic FSA. Otherwise, every deterministic FSA by default is a non-deterministic FSA, and for every NFSA, we can very well construct a DFSA. Otherwise, the power of both deterministic and non-deterministic FSA are equal. Okay, so we were mentioning about the limitation of the earlier example to construct this language. So the problem is because lack of its memory. Suppose I enhance memory of the machine. Can I accept this language? Yes, it is possible. So what do I do? Apart from the routine input string, control, and a pointer head, I'm attaching an extra memory, which is called stack memory. This stack is basically like a record book. It can simply record what happened in the process. It can make note of the progress of the functioning. Like the FSA, it has got a semi-infinite input state, and the pointer head can point at a symbol, one symbol at a time, and keeps moving right side. There's an add-on stack, alloc memory. And each move depends on not just the input symbol alone. It depends on the input symbol and the topmost stack symbol. In the stack, the topmost symbol is only visible. It is accessible to the machine. So the control will check the input symbol, will check the topmost symbol before making the next move. Well, this is a formal definition. Let's have the formal definition will have Q, sigma, gamma. Gamma is the stack symbol. Because we have got extra stack now. So this gamma can have its own stack symbols. Then Q naught is the start state, and Z is the topmost stack symbol. And of course, F as usual, set of final states. Let's run this example, A power n, B power n. This is a usual FSA, but we are adding on the stack. I am placing when n equal to 3, A cube, B cube. There is 3 A's followed by 3 B's. This word was not possible by the FSA before because it has remember how many A's it had read so far to accept exactly that number of B's. Okay, this blue B's are basically blank symbols, not confused with this B. There are blanks, nothing there, blank. Okay. Now, the start state is Q naught, and we are saying Q3 is the final state. A, B are input symbols. In the stack, I'm using 3 symbols, Z0, capital A, and capital B. And this how there are basically 5 transitions. If you look at carefully here, there's a small difference in the expression. Delta, a state, input symbol, and the topmost stack symbol. It means when the machine is in state Q0, taking input symbol A and Z0 being the topmost stack symbol, the machine can move to the state Q1 and add capital A and place capital A on top of Z0. You can imagine that when you place something on top of this one, the whole thing will just drop by one place. The capital A will sit on top of Z0. So this is the state diagram. When the machine is state Q0, scanning a symbol A, as I mentioned here. If Z0 is a topmost stack symbol, as I mentioned here, it can go to state Q1 by placing A on top of Z0, A on top of Z0. Let's just see how the machine is functioning. Well, we are starting now. Everything is set. The machine is set on the start state Q0, which is the start state. And for the input symbol, the pointer is reading the symbol A. While in Q0, scanning A, Z0 being the topmost symbol, as per the transition, it is supposed to move to state Q1 and place a capital A on top of Z0. You please watch here and here and here. The next move, yes, there is this rule is applicable. So while it is in Q0, scanning a symbol A, Z0 being the topmost symbol, it makes a move like this. Look at here, it has become Q1 and the A is placed on top of Z0 and the pointer moves one symbol to the right side. I repeat, first, this is the delta mapping transition that's applicable. This up. And now it is state Q1, scanning A, and topmost is A. So while it's in Q1, scanning A, and topmost being A, it has to place one more A on top of A. That's what it says. Well, in Q1, scanning A being the topmost, it has to place one more A on top of the previous A. Well, in Q1, scanning A being the topmost, it will push further one more A. Now look carefully. This is applicable. This transition applicable. The next move. I repeat the two. The step 1, A is placed. One more is A is placed now. Now, for the third A, the same rules applicable. One more A is placed. Now, you listen here. At the end of in the process, when the 3 A's are scanned, some kind of recording is done. 3 capital A's are placed. So it's an indication that the machine has already scanned 3 small A's. And now it has to read the second half. When it's scanning B, it has to change the role. It has to make a tally mark. It has to make sure that for every A B is kind of tallied. So the role changes now. While it's in Q1, scanning a B and A being the topmost. Well, in Q1, scanning a B, A is the topmost. You find a lambda here. That means whatever be the topmost, you remove that. You remove that. That's the meaning for this lambda. So when you remove this topmost A, the whole thing will pop up. Look up here now. Yes, the whole thing is popping up. Now, again, it is in Q2, scanning B. If A is on topmost, remove that A also. So this A will be removed and this thing will be popping up. Yeah. Yes. And for the one more B, yeah. And now the whole string is read, and now we're just jumping off the string. It's just scanning a blank. Well, scanning a blank, that's I put as lambda here. Z0 is on top. The machine is allowed to go to state Q3, and Q3 is already defined as a final state. So when it reaches the final state, the word A cube, B cube is accepted because that's making the machine move from the start state to the final state. I'll repeat the whole thing. Once you understand, it's easy. Yeah. Yes. Now, I want to design another PDA which will accept a power n, b power 2n. Let's see how, I mean, this is another language for which I have to find another machine. So this time I have made some modification here. You find some changes here. And for n equal to 2, I have a square b power 4. So I'm placing a, b, 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 b in the input string. And the rules are changed now. That means when you are on state Q0 and you scan a and Z0 is the topmost, you are placing two capital A's on top of Z0. When you scan A and when you have A as topmost, you place two A's on top of the earlier A. That means for every A, you're basically making two capital A's in the stack. So that when two A's are scanned, already four capital A's will be there. That for each capital A, you can tally one small b, one small b. That's the idea. Let's just run. Now I'm placing this rule is applicable because it's state Q0. Scanning is a symbol A, topmost being Z0. It has to make a move to the state Q1. It has to place two capital A's on top of this Z0. Yes. And now it is state Q1. Scanning A on the previous A, it has placed two fresh A's on top. So what happens? Look here. Yes. Now there are four A's placed. While scanning a B, now it has to start removing this A for every B. So while in state Q1, scanning a B, it has to remove the topmost A. So now you have only three A's. And now second A is removed. Third B is removed. And the last A is removed. It is going off. And at the end of scanning, there's nothing there blank, which is lambda. Z0 is on top. The machine is allowed to go to the state Q3, which is the final state. Q3 is the final state. So the word is now accepted. So this machine is designed to accept the language A power n, B power 2n. Now I want to test whether we can find a PDA to accept A power n, B power n, C power n. But if you try, you will fail miserably because PDA cannot handle a language of this type. That means PDA also has its own limitation. Like we said, determinism in regular language in FSA. Here also we can talk about non-deterministic PDA, deterministic PDA, but you will find that the NPDA or NDPDA is more powerful than deterministic PDA version here. Well, we are not going to that detail now. Now, this PDA is also has own limitation. So naturally, you have to look for a much bigger machine. Something called linear bounded automaton is much powerful, but we are going to much more powerful machine, which is known as the Turing machine. A Turing machine will have 7 components, set of states, input symbols, but you don't find any stack here. Instead, we're enhancing the power of the pointer. The power of the pointer is enhanced to read a symbol, to erase a symbol, to rewrite a fresh symbol, and the head can move both right side and left side or can stay. So it's a two-way, it can move. The point head can move right side or left side. And so the input tape is basically, it's not semi-infinite, it is infinite in nature. And the pointer head at the tape can read, erase, rewrite one cell at a time, and it can move either left or right or can stay in the same cell at that moment. Well, we have a control unit which has a state and the delta transitions imbibed. Let's see. This is a formal definition. So here, the gamma talks about all the special symbols I can use on the tape for rewriting purpose. So even I can use blank as allowed symbols, a special symbol here. Let's see. I want to run a machine, a Turing machine, to do the binary addition. We all know that this is the binary number for a corresponding decimal number. By binary incrementer, we mean that with this number, a 1 can be added. for this binary digit 100110, the next number should be 100110. So here is a Turing machine that can take this as the input and give me the output 100111. These are the rules. Let's see the rule here. Slightly different here. If you look at this, slightly different. It says when the machine is in state Q naught, scanning a 0, it will keep the 0 as it is 0, and the pointer head can move right. Suppose the machine is in state Q1. If it is taking 1 as an input symbol, it will replace the 1 by 0, and the pointer head can move left. So this is the indication. The same thing here. While in state Q0, scanning a blank symbol, you can go to state Q1. The blank can remain as blank. The header can move left. So we are indicating the movement also on the right side here, the next move. So we are going to use 0, 1, and this small square as a special symbol on the tape for rewriting purpose. Let's run now. I'm having a Turing machine whose job is to find the increment of the given binary number. Start state is Q0. It is supposed to reach the final state Q2 based on these transitions. This corresponding diagram, both are the same. Well, I'm placing this as the input on the input tape. Because both sets are infinite, I'm just kind of placing a blank special symbol here. But the pointer head is placed on the leftmost non-blank input, which is 1 here. So we are about to start. Start state Q0. Input tape is having the input string. It is pointing at 1. And now, this is how it begins. It's in Q0, scanning 1. It is supposed to be in the same state. Don't alter 1B1. Move the pointer head 1 cell to the right side. So look at the pointer now. Yes. And now it is state Q0, scanning a 0, which means this rule is applicable. It's in state Q0, scanning a 0. It will remain the same state. It does not alter 0, 0 as 0, moves right. Now, this rule is applicable. It's in Q0, scanning a 0, doesn't alter, move. And now it scans this 1, doesn't alter, doesn't alter. And now when it is scan 0, it keeps going. It is off the input tape, but this Turing machine can come back. It can move left. Therefore, when it is scanning the blank symbol, while set Q0 scanning a blank, it can move left. Doesn't alter the blank, but the point head can move left. Now, and it changes state from Q0 to Q1 also. You look at here, here, next. Yes, it's coming back to the track now. And it's an incrementer. It is supposed to change this 1 to 0 to 1. So the next step, it is making the last 0 to 1. Yes, and going to state Q2. Q2, we have already said as final state. So at the end of at the end of this process, it has reached a final state. When it reaches a final state, what is shown is the output. So in Turing machine, the output is shown on the very tape here. This is a binary. So we had the input string 100,110, and output string is 100,111 as the output. Suppose I have another input string, say this time 100,111. How it moves? Closely follow. Yes. It is supposed to scan the whole thing right. At the end of scanning, it come back. It look for this 1. It has to add 1. This becomes 0. Then what will become? This will be added 1 here. So it has to change this 0, 1 to 0, and then it will become 0. This will become 0. This will become 1. Notice carefully. As it runs, it scans, jumps right, jumps right, goes off the string, and it comes back. And this time, this one has to be incremented to 0. And when you in the binary addition, that one is carried over, this becomes 0, and the one is carried over, 1 plus 1, 0 here, and then this 0 becomes 1. Once it becomes 0, it has reached the final state, Q2. The moment it reaches the final state, it has to stop the process. So at the end of, once it reaches final state, this is what you get as the output. For the input, you get the output. One more illustration. This time I'm just giving 1, 1, 1. We know that when you add the increment here, this becomes 0, this becomes 0, this becomes 0, and then this has to become 1. So the machine has to come right through and then moves, make it 0, then this 0, 0, and then this blank is made into a 1. At that time, it reaches the final state. So for the input string, the binary incrementer gives 1, 0, 0, 0. Right. Now, I'm going to talk about how a machine can be made to compute functions. Here is a function, f of x equal to x plus 2. For a given natural number, how will you make the machine compute a function? Well, we have a problem here. I'm giving input value 6, not in the binary form. I'm going to express the 6 in terms of some representation. Let me express the number 6 in terms of 6 A's here. So I'm going to tell the machine that to represent the number 6, I'm going to give 6 A's. Suppose I want to give an input 10, then I have to put 10 A's. So the computer function, this x is the input, and this is the output, expected output. So look at the rules here. These are rules, very simple 3 rules. Very just 3 rules. This machine is able to compute the function x plus 2. I'm giving you input sample 6, and the machine has to give me the answer. Well, we know the answer is 8. If I express 6 as 6 A's, then naturally the machine will respond with the answer 8 A's, because 8 is the answer. So how will the machine changes 6 A's into 8 A's? Basically, taking the 6 A's, the number 6 input, the machine has to work and find and make out 8 A's. That is the x plus 2. So the machine will scan all these A's one by one, doesn't alter. The moment it goes off the string, it will make this blank into a A, then again move right, make this blank into A, and then stop. Otherwise, it has simply go through entire string, then just go off the string twice, make the 2 blanks into A's, the non-existing blanks into A's, so that you have 8 A's. This is what it happens. Let's just see. Yes. When it comes here, it scans a blank. It makes the blank into a A and moves right. And then one more blank. In the meantime, it's going to change state Q1. So this is a trick here. To have a control on reading exactly 2 blanks, it moved from state Q0 to Q1 and Q1 to Q2, making one more blank into A. And when it is Q2, we have set Q2 as final state. So you have to tell which is the final state. And at the end of the process, it is showing 8 A's, which is the output. How will I make a machine, a new machine, to compute x minus 2? Well, suppose, this can run for x greater than or equal to 2. Suppose I'm giving an input 6 A's, it has to remove the last 2 A's. How will it run? It has scanned the entire 6 A's and then come back, remove the A, make a A into a blank. Make this A also into blank. This is how it'll do. And now one more example. We are almost reaching the final. Suppose we are given 2 natural numbers, x and y. How will I express 2 natural numbers? As a function, f of x and y is x plus y. I'm going to use first part of the string, a, to express the first number, x. Then I'm going to use a special symbol p. Maybe p stands for plus. And then to express y, suppose I have 3, I put 3 A's here. So 2 plus 3 is expressed as 2 A's, P, 3 A's. So this is how I express the input data. And well, the answer is 5. So the machine is supposed to give me the answer. It might give 5 A's. So how will the machine convert these 2A, P, and the 3 A's into 5 A's? Well, it has to run through from left to right, and then it has to identify this P. It has to remove this P, bring all the A's here, so that it can have continuously 5 A's, which is the answer. So these are the rules involved in making this process. Let's just have a test run on f of 2, 3. It is scanning. First A, second A, and then P. And the machine is already designed for addition. So it will make the P into A. And the last A, it will remove a blank. This is the idea. Okay, I repeat. Sorry, with the previous one. Yeah. Here, ultimately, I have to remove this P and make this place for a A and remove this A so that I have consecutive 5 A's. So that's what's done by the machine. First A ignores jumps, second A ignores that the P is now made into A. It has to keep in mind that a P is removed, so it has to remove A here. So it goes, and once it jumps off the string, it comes back and it removes that A into blank. Once it does, it is reaching the final state. So the machine is made to reach the final state once this process is done. Output is 5. Well, so it is possible to think of addition, subtraction, multiplication, division. Once we design a kind of machines for these 4 basic arithmetic operations, any big formula, maybe a function of log or exponential, anything can be made up of these 4 basic operations. So any bigger function can incorporate all these basic arithmetic operations, and a bigger machine can be constructed. Well, we have seen basically the family of FSA, family of PDA. Of course, the linear bound automata we didn't touch upon. It is basically like a Turing machine, but slightly less powerful. So we have basically mentioned about 4 classes of automata. And we have seen example for FSA. We have seen example for PDA. We can find examples of, well, we have given examples for Turing machines also. So if you look at this one, well, we have used a function to be computed. This example is found here, for which I cannot find a LBA, neither PDA nor FSA. Only a powerful machine can handle powerful problems. But there may be problems beyond the scope of Turing machine as well. So that talks about the limitation of Turing machine. And so we talk about the desirability. A problem is said to be desirable if there exists a Turing machine that halts and gives a definite answer, either yes or no, for every statement in the domain of the problem. So if you can have a definite answer, either yes or no, for every problem in the domain, then the problem is said to be desirable. So such problems are called Turing desirable. That means a Turing machine will always stop and giving us a definite answer, either accepting or rejecting. So we are sure about the response. We have already seen about the family of regular languages, whether the family has, the language is empty or not can be decided, because when we have a regular language, it'll have a corresponding FSA, it'll have a corresponding state diagram. The state diagram will have a start state, final state. If you have a sequence from start state to final state, that means you're able to kind of get a sequence of strings. If you get a sequence of strings, that means there is a string. If you're unable to reach the final state, that means there is no string. So the emptiness can be decided for the family of regular languages. So the emptiness problem for family of regular languages is decidable. Whereas I have a small bit of procedure which we give. That means we are having a small procedure starting with the input value n, which should be greater than 1. It can be any natural number more than 1. And for the starting given number, the procedure will divide into half if the number is even. So it will generate a new number, half of its size if n happens to be even. If the number is odd, it will make 3 times of it and add 1. Well, this is basically the famous Collat's sequence of numbers. Let's see how it works. The issue is, when you generate the sequence, will the sequence stop or continue? Let's just try with 7. 7 is an odd number. If it's odd, it has to make 3 times of it plus 1. So 3 times of 7 is 21 plus 1, 22. And 22 is greater than 1. So it's again put into the procedure. A new number is generated. This time 22 is even. If it's even, reduced by half. 11 is a new number. 11 is still greater than 1. So it's varied again. 11 is odd. So 3 times of 11 is 33 plus 1, 34. So you get a new sequence generated, 34, 17, 52, 26, 13, and so on. And then it keeps going, 16, 8, 4, 4 is even, then even 1. When n is 1, this fails. While n is greater than only, it can continue. When it becomes equal to 1, this fails, comes out of the procedure, and the sequence stops here. Let's try with another number, say 100. Suppose I try with 100. 100 is an even number. So it becomes 50, then 25, then 3 times of 25 is 75 plus 1, 76. It goes on. You find that also comes back and stops at 1. Well, whatever the number we try, we find that it comes to that 1. It stops. But does it terminate in general for any input, any number? No, we haven't found any method that will guarantee that one. That means this halting cannot be decided. There exists no method that decides if this procedure terminates or not on any arbitrary input. So, in other words, this famous problem, halting problem, is undesirable, can be stated here. Such problems are called halting problems. We cannot decide whether the halting is guaranteed or not. Well, this picture is now known to us now. We can find problems beyond the scope of Turing machines, but there are more than many problems beyond the scope of Turing machines. Yes. Well, I'm almost at the end. We have seen the FSA and PDA. In the text search of a given passage, especially when you search for a word in the text file or in a file, or when you search for a word in the browser, you have to find the proper matching. It's called pattern matching. And the very FSA is very much useful designing algorithm for pattern matching algorithms. And when it comes to the DNA sequence analysis, we look for a proper combination of the nucleotide compounds, that is GC. And that is also done by an FSA machine. In the area of compiler construction, of course, we have the lexical analyzer or syntax analyzer. The PDAs or FSAs are very much effectively used in the compiler construction. Something called the inference algorithms or learning theory, we rely on such FSA machines. In model checking, we talk about infinite words for which a special automata called Bushy automata are constructed, and they are used in the specification or correctness of systems. And to talk about pictures generation or recognition of characters, there are two-dimensional and high-dimensional automata as well. So these are some of the variants of machines that can be used in the study of other areas of automata theory. There are many books available, but these are the 3 books which I had referred. Well, in case you have queries, you can ask now. But if your queries are more number, please note on my email ID or my WhatsApp number. You can text me. Thank you for listening. I stop here, and I am open for some of your questions. Well, I think I had run almost 1 hour and 20 minutes. It's a long lecture. Well, now over to the audience for the response.
So thank you, sir, for this very interesting talk and a very clear session. If you have any feedback questions, you can put it up. Any questions to be answered, the feedback link is also given on the chat. We will give you a half an hour time to slowly post. After the session is over, you have a half an hour more time to give your feedback forms. If there are any questions, you can please share it now. Sir will be willing to answer. Sir, I think one question was someone asked if on the final state, can you have a loop in a finite state automaton?
It is very much possible. You can have very much loop in any of the states, including final states. Yes.
Mr. Subramanian wants to know if you can tell any book for introduction to the automata theory.
Well, the book I mentioned by Peter Linz, I hope you have seen the 3 books. The book authored by Peter Linz gives an approach on the automata studies. I think that's a good book to start with. And also the book by Michael Sipser is also a good one.
Another question is it possible to have a state as both final and start state?
Yes, it is very much possible. If you may recall one of the examples that we did, a power n, when n varies from 0 onwards, the Q1 happens to be both final as well as start state. It is possible to have, if in case you want to accept a lambda, an empty word, then your initial state has to be final state. Yes.
Any research papers available in automata? I think
there are thousands or tens of thousands. Just a Google search would fetch you an ocean of papers. Yeah. Well, but the automata theory is basically a broad area. There are a lot of branches,
As we are running short of time, I think they can forward the questions to sir by mail or by WhatsApp. We can also forward the numbers to you if you ask us. We will now move on to the vote of thanks. I request Dr. Vasanthi Pula, Assistant Professor of the Department of Mathematics, to propose the vote of thanks.
Thank you, Emerald. Happy evening to all. It's my great pleasure to thank our resource person, Dr. Robinson Tamburaj, Associate Professor and Head, Department of Mathematics, Madras Christian College, Tambaram, for his excellent presentation and talk on Introduction to the Theory of Automata and its Applications. I'm sure this talk would certainly be an eye-opener for many beginners. Thank you, sir. Next, I thank our Principal in charge, Dr. Varalakshmi Anandakumar Madam, for her constant support in organizing this webinar. My sincere thanks to Dr. Vijaya, Associate Professor and Head, PG and Research Department of Mathematics, Queen Mary's College, Chennai, for her motivation and the determination in organizing this event. I place on record my sincere thanks to Emerald Princess Sheila, Assistant Professor, Department of Mathematics, for her tireless work in bringing out this webinar a grand success. It is my duty to thank her son, Mr. J. Jonathan Samuel, and also one more person, Mr. A. Murthy Ilamaran, son of Dr. Vijaya, for their technical and organizing support. I also thank Dr. Punitavati, Associate Professor, who motivated us along with our HOD in various ways. I also thank all the faculty members of the department for their support. Finally, on behalf of our principal, HOD, members of faculty and students, I thank all the professors from various colleges, research scholars and students, and of course, all the participants across the country and abroad for the active participation in this webinar on Introduction to the Theory of Automata and its Applications. Thank you. Requesting all once again to kindly fill the feedback form without any error in name, as the same would be reflected in your certificate. Thank you. Stay home, stay safe.
Yeah, thank you once again for all the participants, and we thank you very much, sir, for the very clear presentation. Signing off now, Mrs. Emerald Solomon, Department of Mathematics, QMC. Thank you.
Thank you, sir.
Thank you.